The Moss Report is brought to you by MycoLife, makers of the world's best mushroom extracts, including the Moss Method mushroom formula, available exclusively at mycolife.us. In August of 2025, my father and I sat down with Professor Thomas Seyfried of Boston College to get an update on his research into mitochondrial and metabolic theory of cancer. As we were talking, one name kept coming up, a colleague of his in Budapest, Hungary, who occupied something of a pivotal role in the development of this important work. A few months later, in October, I flew to Budapest to interview him. I'll share that conversation with you in a moment, but first, here is Professor Seyfried from that earlier interview. Link to the full video in the description.
There's now massive evidence presented that all major cancers have some defect in the number, structure, and function of the mitochondria, all of which creates an environment where mutations occur as a downstream effect of the damage to the regulation of energy metabolism. Otto Warburg was the first to discover the origin of cancer as a mitochondrial metabolic disease back in the 1920s and 30s. But his failure to recognize that there is a second fermentable fuel, which is glutamine, and the mechanism for that, which is mitochondrial substrate-level phosphorylation, was not known to him. We teamed up with Christos Chinopoulos, the world expert on mitochondrial substrate-level phosphorylation, which is a fermentation mechanism inside the mitochondrion itself. So these cancer cells are doing nothing more than falling back on these ancient fermentation pathways. Christos Chinopoulos at Semmelweis University, who is the world leader on understanding substrate-level phosphorylation, he looked at my diagram. He says, no, that's not right. So, but he said, your idea is really exciting, but he said, the pathway you have is not right. So we then, over the last 15 years, designed experiments to get to the right pathway and then figuring it out. Warburg was correct. He just didn't have all the stuff put together. So we can take the whole cancer field and put it back on the right track. The mitochondrial metabolic theory will replace the somatic mutation theory and all other theories because it's the only theory that it can account best for the facts of the disease. I don't give a damn what anybody says. I mean, this is absolutely a mitochondrial metabolic disease, which now opens a whole new world of way to attack this problem.
Hello healers, my name is Ben and this is the Moss Report. I'm here in Budapest, Hungary, outside of Semmelweis University, where we're going to be meeting with Dr. Christos Chinopoulos, who is a world-renowned biochemist, researcher, and professor here at the university. And we're going to be discussing his ideas and his research into mitochondrial and metabolic theory of cancer. So we'll go inside now and we'll meet with Dr. Chinopoulos. Dr. Chinopoulos, thank you very much for seeing us.
My pleasure.
Taking the time out of your busy schedule. So how many students are here at the university?
Okay, so we have 3 faculties.
Okay.
English, Hungarian, and German.
Okay.
And there are, there are 500 medical biochemistry students, English, about double Hungarian, and about 300 German.
Wow.
Almost, that's for
wow. Almost 2,000 students.
Yeah, but this is only for biochemistry, but you have many other faculties.
That's only in biochemistry.
Yes.
So that must be the biggest biochemistry department in Europe.
Well,
or one of them anyway.
Yes, we have a lot. So the construction that you see over there, it is the building 2 being built.
Oh, wow.
We're going to increase the number of the students admitted 2 times.
Professor, thank you so much for taking the time to talk with us.
Thank you for coming over here.
Recently, we had a conversation with Professor Thomas Seyfried.
Okay.
Fascinating conversation. My father and myself and Dr. Seyfried sat down. He brought us up to speed with what his developments at Boston College are in terms of furthering the understanding of the mitochondrial and metabolic theory, as he calls it. Is that the same thing that you feel like you're working on here? Is it the same terminology?
Yes, we are absolutely on the same page with Professor Seyfried, with Tom. We speak very often on the same subject, especially even today in the afternoon. His student is having his Ph.D. defense, on which I'm an opponent, and exactly on the topic that you just mentioned. So ever since I talked with Professor Seyfried, we are exactly on the same page, exactly on the mitochondrial aspect of cancer and how can cancer be dealt with from the metabolic aspect of view. We have a few, of course, scientific-based disagreements, obviously, but otherwise, yes, we are foot soldiers on the same battle.
Well, he spoke very highly of you. In fact, he credited you with having sort of helped him, review his own theory and his own research, and maybe collaborate on some ideas. And when I heard him mention you, it just sounded like it would be great to come here and talk with you a little bit about the type of work that you're doing. And you've just gotten done telling me that in this university, there's over almost 2,000 students in biochemistry alone at this university, which is amazing. And you have a central role here, both in the administration, but your primary role is as a researcher.
Yes, my primary role is heading the, let's say, the oncometabolism unit of the biochemistry department. It wasn't always the case. I originally started from neurodegenerative diseases, the mitochondrial aspect of neurodegenerative diseases.
Interesting.
But I realized that all those metabolic pathways that I thought need to be rescued in order to cure or prevent a neurodegenerative disease would be the exact same pathways that the cancer would use to thrive in adverse macroenvironments. So I made the jump about 15 years ago from neurodegeneration to cancer metabolism. And it has been I think a pretty good jump because unfortunately with neurodegeneration you can't really help people as a preventive measure, but you can for cancer patients. There's a lot that can be done from the metabolic and mitochondrial aspect on cancer patients.
And one of the topics that we discussed with Professor Seyfried was how the work that he's doing and that you're doing is building on and in some ways correcting the work of the Nobel Prize winning scientist Otto Warburg. Do you feel as though you've made some real leaps and bounds in terms of advancing the discoveries that he came up with, and what would those advancements be?
Yes, so we do have contributions, no matter how small they may be, but we do have contributions in highlighting the importance of metabolism on cancer. Luckily, we are not the only ones. But unfortunately, this subfield has not gained sufficient traction yet. You can see it on the level of advancement preclinically, which is huge, but does not yet apply on clinical trials. So that means that the general public, or let's say lawmakers, or even clinical doctors do not really adopt the possibility that there can be and there should be an aspect of treating a cancer patient from the metabolic point of view. A main concern of an oncologist, of a current oncologist or a surgeon, is that a cancer patient has to eat well. Okay, you have to avoid cachexia. And that is very difficult to go against and tell to the caring physician that your patient has to actually go on a diet, a ketogenic diet. That's very hard to pass. So So we have to. Professor Seyfried and I are working on proving, on proving scientifically, and others, of course, as well, how important it is to enforce metabolic aspects on a therapeutic level on cancer patients.
Okay. So the work that you're doing is mostly laboratory work. It's not clinical studies. Is that right?
Yes, that's correct. I do have a couple of levels of interaction in the clinic. One is that we receive a lot of human tumor material, for which we do, you can say, basic biochemical work, but it can be used for diagnostic purposes as well.
Okay.
And plus, we have a drug in a pipeline that I'm very much hope to collaborate with someone who has hands-on and can try such a drug.
So there's two aspects of how cancer cells get their energy: through glycolysis, through conversion of glucose into energy, which is something that healthy cells also do. But cancer cells being a little bit different, or maybe significantly different from healthy cells, they're also using glutamine and fermenting glutamine to produce energy, which the way that Professor Seyfried described it is sort of a holdover from an ancient, way of having energy for microorganisms. And the issue that it seems to be focused on right now is, okay, if we have a ketogenic diet, we can affect the amount of glucose in the body by getting into nutritional ketosis. So we have the ability to reduce the amount of glucose coming in and feeding the cancer for its growth. But we don't really seem to have yet the ability to effectively and in a non-toxic way or a less toxic way affect the glutaminolysis pathway, the ability of the cancer to ferment glutamine, the amino acid glutamine, to convert that into energy, and glutamine being the most abundant amino acid in the body. Anyway, this is what I understand is the challenge. Is that a fair summation of the type of thinking about this that
Yes,
you have as well?
Okay, so let me put it a little bit on.
Please do.
Yeah.
Thank you. I appreciate the education.
Okay, so it is an oversimplification, but this concept is correct, that the tumor and of course highly proliferating cells as well require glucose and glutamine. Obviously, other things are required as well. Okay, and it is not really possible to cut down or prevent the provision of glutamine to cancer cells.
Okay.
And also, it is also not possible, I think, to prevent or to diminish the provision of glucose as well, no matter how much, how strong a person can indulge in ketogenic diet. However, having said that, it is very, very helping for the patient to do the ketogenic diet because of the so-called ancillary effects. Mm-hmm. The ancillary effects are many. I will just tell them as simple as possible. Mm-hmm. One of them is that the ketones formed in the body themselves, they have really, really good effects in fighting cancer. Mm-hmm. One of them is beta-hydroxybutyrate, for example. You may even take this as a supplement, but best way to do this is to do the ketogenic diet. So when you are on a diet, you can decrease glucose concentration in the blood significantly, but I think not to the extent that would not be sufficiently available for the tumor to take up and perform whatever it can do from glycolysis. That's one thing. But having said that, I reiterate that going into a ketogenic diet, it's an absolute must. I think it has to be implemented in the vast majority of cancer patients. There is a very minor fraction of cancer patients that would not benefit from ketogenic diet, but the vast majority would be would see an additive, if not synergetic therapeutic benefit from whatever chemotherapy or radiotherapy regime they are getting. And the other thing what you mentioned about...
Yes? Let me pause you. So if I'm understanding you correctly, you're saying that it's the presence of the ketones that has an anti-cancer effect,
What,
not
yes.
necessarily the nutrients or the other aspects of reducing glucose that ketogenic
Yes.
diet might.
Presence of ketones, that's one thing.
Yes.
The other one is the obesity is a kind of a pro-inflammatory state.
Right.
So if you decrease obesity, you push your body to secrete a type of substances that are anti-inflammatory. If you are obese, you are actually into a kind of a chronic inflammatory state. So if you lose weight, you helped against the inflammation. Inflammation is bad, generally speaking. It's for most types of cancer.
Right.
That's one aspect. So ketosis, anti-inflammatory signals. Other ones are that when you eat glucose, then in order for glucose to be assimilated into certain types of cells, you need to produce insulin as well. And insulin has effects other than introducing glucose into the cell. And these insulin effects are helping cancers to grow and metastasize very strongly.
Really?
So if you don't eat glucose, you don't produce the insulin, which doesn't have the cancer increasing effects.
Now, is this part of what you have personally researched and discovered?
No, that's not our field.
Okay.
I do write reviews about it.
Okay.
And this is something that we teach in our curriculum as well.
Okay. So where is that primarily being? Where is that information about insulin being?
This is actually not a new thing.
Okay.
So it is a positive byproduct of not eating glucose, that you don't have insulin that would stimulate the cancer cells to proliferate and metastasize.
I see. I did not know that.
Yes, and it's not just the insulin, but it's also there are proteins that bind insulin and also bind insulin-like proteins, and these are called the insulin-like proteins. These are called insulin-like growth factors. So when you eat glucose, you have increase in insulin. Okay, you have increase in insulin-like growth factors, and you have increase in the insulin-like growth factors binding proteins. All these three things, they tell the cancer, grow up. So if you don't eat glucose, you don't have any of those. And on the other hand as well, if you don't have insulin, you have glucagon, and glucagon has inhibitory effects. So overall, it's really good not to eat glucose. Very good to go into ketogenic diet because of a bit of, for example, ketone body production. So, but I don't think it helps from the point of view that you can limit the amount of glucose that can enter a solid tumor or a liquid tumor, like a blood tumor. So I agree completely with Seyfried that people should not eat sugar at all. They should go on a ketogenic diet. I disagree partially with him regarding as of why, but I don't think it matters. Just to go on a ketogenic diet.
Okay. Now, you had mentioned that you're doing some drug development.
Yes.
So Professor Seyfried mentioned that he was doing some laboratory research with mice utilizing a fairly toxic form of chemotherapy called DON, which I can't remember the full name of. I'm sure you know it.
Yeah.
But that what struck me was that the toxicity level of that drug in the mouse model was lower when the mice were in ketosis.
Yes.
Fascinating.
Yes. So, and this is true not just for this drug, but for other drugs as well, and also for radiotherapy as well. So, ketogenic diet helps to decrease the dose of the chemotherapeutic agent, which means less side effects, and also assists in radiotherapy. So you have to irradiate patients at lower amounts.
Okay.
So ketogenic diet is doing it by many different ways. One is because ketogenic diet strengthens your immune system. You want to have a really strong immune system to fight the problems that chemotherapy and radiotherapy exerts on the.
As we know, chemotherapy can be very immune suppressive.
Yes. Now the problem with DON is two main problems. One is that the normal immune cells that fight cancer are also dependent on glutaminolysis. So if you give the drug that inhibits glutaminolysis, you don't inhibit just the cancer, but you inhibit your own cells requiring glutaminolysis. That's one thing. And the other thing is...
Lymphocytes and dendritic cells, perhaps? Or
yes,
just right across the board?
Well, across the board, but some, of course, some cells are more important than others.
Right, so it's immune suppressive.
Yes, it will have an immune suppressive, which you don't want.
No.
And the other problem with DON is that you want to prevent a catabolite of glutamine inside the cell from entering the glutaminolysis pathway, and DON blocks only one pathway of glutamine entering the cell. So you still have the other one. Okay. So, I mean, as an adjuvant therapy, DON is okay, but there are these two problems. You cannot add too much because you kill your immune cells.
Right.
And even if you add too much, you won't be able to block glutaminolysis completely.
Now, I don't want to pry too much into your intellectual property. Obviously, you're in drug
No, I will
development. You can't,
I will
disclose too much, I would think.
Wait. That's important that you bring it up.
Okay.
I'm not going to patent the drug.
Oh, no.
No.
Really?
Yeah.
Oh, wow.
I'm not after the money.
Okay.
Because if I patent the drug, then it's going to, that doesn't help people. It takes a lot of time. To me, it doesn't make any sense. I don't care. I'm not after the money. If I were after the money, I wouldn't be sitting here. I would be in finance or something else. So the drug...
Well, thank you.
If it works.
No, well,
thank me after it works.
Thank you for doing the work and for your commitment to furthering the science as a goal rather than the profit aspect of it.
Because you're welcome.
It's really, it warms my heart, truly.
I'm glad you say this. That wasn't my goal, but I'm glad you say this. So the drug inhibits something much more downstream. So you have, let's say, okay, DON inhibits path A, but you have path B, you have path C. So this drug inhibits something quite downstream. And luckily, that downstream path is not so important for the immune cell, but I believe it's very critically important for the cancer cell. And Professor Seyfried knows this pathway. This is called the substrate-level phosphorylation.
Right. We discussed that a little bit.
So we have been able to manufacture such a drug, identified first from a library, and manufactured. And within the next few months, we will be testing it on cancer models. Okay. Hopefully see.
Well, of course, we wish you the best of luck with that research. Was that based off of something that was in existence already? Is it based off of a repurposed drug that you're modifying? Or really, did you come up with this from scratch based on what you know about that particular pathway and things that can affect it?
Okay, so the desire of having a drug against this pathway has been a desire of mine since I started this cancer metabolism.
So about 15 years ago.
Yeah, because I saw from neurodegenerative pathways that substrate-level phosphorylation helps cells which are in a very bad shape. And then I see that cancer cells use the exact same pathway to thrive under adverse conditions. So I always wanted to do that. So we started trying first small drug libraries, okay? But small drug libraries in the order of thousands, and even though the number sounds much, but it isn't. So if you really want to screen drugs that you may find a hit, you have to go into the millions. And recently there was a protocol which was, I think, implemented by an American company, which is called DNA encoded library. So the DNA encoded libraries, what they have is that they manufacture 10 million compounds. Okay, they put it into a single vial, and then each compound has attached on it a DNA sequence. Okay, then what you do is that you add your target to your vial. And if something will bind strongly to your target, then you elute it. It means you just wash it off. And then you just have to identify the DNA sequence. And you go back into the table and you find out, okay, it was this sequence, so it was that drug.
Wow.
And then you go into a chemist and you tell him, okay, can you please make this for me? Which is usually simple because, I mean, out of the 10 million compounds that they made, they obviously show something which is easy to do. And then once you identify the molecule and you say, okay, it has some activity, then you can start working on altering that molecule. Put a methyl group there, put a double bond there, things like that. But at least you have a so-called hit. Okay, and then you go from hit to lead. So with that, we have been able to, I got a grant a couple of years ago in purchasing the library because the library was expensive.
Sure.
And then we got 5 hits, and they have been, we have been able to manufacture them, I think, 3 out of 5 last month. And we are going to be starting testing them on cancer models as well. Of course, if it works on cancer models, meaning on cell cultures, It doesn't mean it's going to work in a multicellular organism. Doesn't mean it's going to work on
Right.
mice, humans, and everything.
Right.
But we will cross that bridge when we get there.
What you said was that it's not targeting the glutaminolysis pathway. You said it's something that's downstream of that. Can you elaborate a little bit more on what that means?
Okay, so the glutaminolysis pathway means that you take glutamine, and from the glutamine you are going to branch practically into two things. One is into making lipids, and one will be for making a little bit of ATP without requiring oxygen in the process.
Right.
Okay, and this is called substrate-level phosphorylation.
Right.
However, the substrate-level phosphorylation is important because not just from the point of view that it gives you energy in the form of ATP, but it does that in a very small compartment, which is the mitochondrion.
Mm-hmm.
So the mitochondrion, there are several hundred mitochondria per cell, but their volume is much smaller than that of the volume of the whole cell. So what happens is that you are having formation of ATP within a very small volume. That means that you have immediately a very rapid increase in the concentration, because you simply have very few of something, but in a very small space. That means you have an increase in local concentration, and that has a great effect on several mechanisms inside and outside mitochondria. One of the most important mechanisms is that preventing mitochondria from becoming ATP consumers. So mitochondria are made to give us ATP, but if conditions are not optimal, they are very punishing. They are going to consume ATP. They are going to be ATP sinks. Mm-hmm. And if you provide ATP locally within mitochondria, that is going to maintain them as ATP producers, not consumers. Mm. So this is something I think that cancer cells rely very much, because cancer cells rely on biosynthetic pathways. I mean, more cancer cell means they have to make more membranes, more organelles, more this, more that.
Right.
And you need
lots of energy
for that. Yes, you need energy. And you don't get this from the so-called traditional oxidative phosphorylation.
Right.
You have to get it from somewhere. And on top of that, you cannot have mitochondria consuming whatever ATP is there if you want to go into biosynthetic processes. So this substrate-level phosphorylation, I believe it's an Achilles heel for cancer cells.
So really, it's about looking at what the essential differences are between a cancer cell and a healthy cell, and
yes,
working to leverage that difference to be able to affect the cancer cell specifically.
Exactly. Now, one aspect, this was one aspect. The other aspect is that normal cells use oxidative phosphorylation.
Right.
They don't care that much if you inhibit substrate-level phosphorylation. So I think that is going to help against having serious side effects.
Right.
So this is the very good thing about this.
Right. So you really feels like you're honing in on the essential difference and how to sort of tweak that to affect the cancer cells specifically without affecting healthy cells.
Yes, and it doesn't need to be a monotherapy. I don't care. Mm-hmm. It can be, as part of polytherapy.
Right. Well, that's again going back to what we were discussing with Professor Seyfried, was that he's looking to also do some things that are a combination therapy.
Yes.
Including ketogenic diet and some kind of a chemical introduced that leverages that difference.
Yes. Well, regarding the other types of therapy these days, so there have been a couple of really good breakthrough discoveries. One of them was that, I do not know if you're familiar with KRAS gene.
I've heard of it.
Okay,
yes.
So KRAS has been considered undruggable for many years, but recently there have been a couple of drugs discovered that they can inhibit KRAS, and they have moved immediately into clinical trials. So usually it takes 7 to 10 years to go into this, but because of the potential positive impact, they have moved immediately into applying this into patients. That's one thing. And the other one is that there has been great improvement in immune checkpoint inhibitors. So these are drugs that they help your immune system to identify and kill specifically the cancer cells.
Right.
So if you have the immune point inhibitors, you have the KRAS inhibitors, you have the ketogenic diet, maybe you are going to have the drug that we are developing or something like this. I think that is going to have a synergetic effect, not an additive effect, in increasing the life expectancy and life quality of cancer patients.
Well, I really love the fact that you brought up the importance of having a healthy immune system and having the immune system be the sort of driving force at getting rid of the cancer once that cancer has been identified. Does your protocol sort of help the body's immune system also recognize this, or would something like a checkpoint inhibitor drug be part of a protocol that would be included in something that is more of a mitochondrial focused?
Right. Well, at the moment, at the very moment, we are not concerned yet of the immune aspect, because we would step too much outside of our expertise and our know-hows.
I understand.
But when we get to the point that we would need to collaborate, let's say, with an onco team, if it is to have our drug as part of the regime, then yes, this is something that we'd have to consider, but not yet.
So I guess the next question that I would want to ask would really be, what is the future of your research here looking like? And it's really a two-part question. So you said you're in drug development, so obviously that's part of it. And you're looking at phosphorylation, that part of it as being a central focus of your research as well.
Yes.
And using the DNA library to try to find hits and then explore those different aspects, right? So is that a fair summary of sort of what the process looks like for you?
Spot on, yes.
Okay.
But we have other leads as well. Regarding, of course, all revolving around the concept of glutaminolysis and substrate-level phosphorylation. There are a couple of drugs which are arsenic-based drugs.
Arsenic?
Yes. So arsenic is a term that
people think it's a poison.
Yes, which actually it is.
Yes.
But it can also be used as an anti-cancer therapy, and there are a couple of them which are FDA and approved agents.
Well, I don't think it should be so surprising, because if you think about how chemotherapy got its origins, I mean, it's toxic.
Yes.
It's a poison.
Yeah. Yes, so, and we have a grant proposal with 4 main institutions. One of them is from Michigan, another one Germany, Greece, and Italy.
Okay.
And they are supplying us with arsenic-based formulations in nanoparticles, liposomes, or conjugated with platinum. With platins, in order to deliver the arsenic in as least concentration as possible, because glutaminolysis is very sensitive to arsenic inhibition.
Oh, interesting.
I think this is the reason why arsenic is very good in killing cancer cells.
Okay.
Of course, it has its own toxicities that has to be kept to a minimum, but that's exactly what we're trying to do.
So once again, leveraging the differences between a healthy cell and a cancer cell.
Everybody on cancer metabolism is trying to leverage the difference, because in cancer metabolism is called rewiring.
Right.
So stem cells or highly proliferating cells and cancer cells, they have things in common, but for adults you don't really have that much of highly proliferating potential. So you don't have cells that exhibit the same principles like the cancer cell. So everybody's trying to leverage on this, see what works in cancer that doesn't really work in normal, and vice versa, and work on that.
We're so interested in this because things like obviously diet that can be done to help a patient, that's one thing that's got low toxicity. Eating a ketogenic diet, I mean, some might say, it's protein heavy, and of course there's very widely diverse schools of thought on the whole subject of diet.
Well, just first of all, ketogenic is not that protein heavy, it's fat heavy, but there are keto versions which are protein heavy.
Okay.
But there are diet regimes that could be used by cancer patients, but they're not widely available. For example, there is a protein regime in which is deficient in the amino acids proline and arginine. And that seems to have a really good effect in xenografts, meaning tumor implanted into animals. Right now, you cannot go into the store and get protein that's deficient in proline and arginine. Okay, and that has to be done under medical supervision. So there are several tricks up the onco team sleeve that can use and leverage this difference, but it's not yet available to the general public. So apart from the ketogenic diet, and of course staying away from all kinds of carbohydrates, the general public does not have an opportunity to do much, but ketogenic and no carbs consumption will help a lot. That should be done.
I was out at a metabolic conference just last week, and a lot of the big thought leaders in the world of integrative medicine have been sort of waving the banner for metabolic therapies for a long time, including, of course, things like IPT, insulin potentiated therapy, and other ways to sort of tweak the metabolism to sort of weaken cancer and then come in with things like low-dose chemo. And that's been the approach. But, I think following your work is going to be a great pleasure, and I hope that we can continue to stay in touch and hear about any developments as they come up. The advancements in things like immunotherapy and metabolic therapies is where the leading edge of integrative, or I guess just cancer treatment as a whole, is heading and should be heading.
Right. I would very much like to see the integration of the recent success of GLP agonists, Wegovy, Ozempic, with cancer therapy.
Okay.
Because, as I mentioned, obesity is a negative factor regarding cancer. And now you are having something that is going to end the obesity pandemic. So I think I would like to see such kind of regimes be mainstream for cancer patients, obviously those who are obese, not for those who are not.
Right. One of the topics that we discussed, which is a little controversial in some quarters, is the use of other repurposed drugs. You're talking about adding an Ozempic maybe as part of a protocol, especially where obesity exists. But it's been floated out there, the use of these other antiparasitic drugs, Fenbendazole and mebendazole. I'm wondering where you land on that subject.
I think that such kind of antiparasitic, antihelmintic drugs could help, but not from the point of view of what people think, because these drugs have side effects of being autophagy inhibitors. Autophagy is a mechanism by which the cell recycles its organelles or eats itself, and cancers rely on autophagy very much. And if you inhibit autophagy, that's bad for cancer. And a known side effects of the antiparasitic drugs is inhibition of autophagy. I believe that this is their means of working, not other means that have been put forward to. So it
which
could,
we discussed as potentially inhibiting the tubules.
Yes, I don't think. I don't. Yes, I don't
so
think.
This is one area where maybe
yes.
it's not quite understood. So.
Yes, I mean, it could be that as well, but I think they work because they inhibit autophagy.
Okay.
So, and the good news about it is that the antiparasitic drugs, they were originally made to inhibit parasitic specific metabolic pathways. So they're not expected to have many side effects.
Right.
Except the one, the autophagy inhibition, which is bad for cancer, so therefore good for the patient.
I've been fascinated by this conversation, and I wish I had more deep understanding of biochemistry.
Actually, you have quite a good understanding.
Oh, well, I do try. I try, So, is there anything else that you'd like to share with our audience about? No? Okay.
No, thank you. That's
all right. Well, Dr. Chinopoulos, it's really been a pleasure meeting with you. Thank you so much for visiting with us and sharing. And of course, we wish you all the best with your research. And we really feel like
thank you.
You're onto something here.
Thank you. I feel the same.
We encourage you in every way we possibly can.
Thank you.
So
If it not come from me, it will definitely come from many laboratories in the world who are working on the same aspect. So,
fantastic.
So it will be on our lifetime.
I certainly hope so. All right.
Let me show you a bit around.
Yeah, please.
Okay. To show. Yeah, this is me 35 years ago.
As a student.
Yes.
Here in this school.
Yes.
You haven't changed much.
Yeah, that's me again. 10 years later.
Okay.
So our department has four main, let's say, subsections. One is cystic fibrosis at TRIMPM2. That's an electrophysiology lab.
Cystic fibrosis electrophysiology lab. Okay.
Yes.
That's down that way.
Yes. And then our section.
What a nice space to work in.
Yeah. So this section is mitochondria, oncometabolism, and also neurodegeneration.
Okay.
So this is just a cell culture facility. This is where we keep most of the cultured cells. So we work with animals and animal models, cell cultures, and frozen human tumor material. So in this facility here, this is called an RPPA facility.
Okay.
And in this fridge and some other ones is where we are keeping the tumor material. The tumor material is being used in such a way that from a single tumor material we can probe it up to 900 times for different proteins.
Okay.
And every time we probe something, we usually do it from almost 1,000 different tumor tissues. So,
And that's using this DNA.
no, that's
a
a
different
different thing.
Okay. So how do you? I'm curious. How do you probe it for?
So we do a so-called we look for a level of protein expression.
Okay.
So what you need to do is that you have to convert the tumor into a liquid form, so you are able to work with it.
Okay.
And then you can print practically.
Let me stop you. So you have frozen tumor tissue.
Yes.
From that, you can grow it. It comes back to life, and you can culture it, or you just have
You
it.
could, but
Okay.
we are receiving it fresh.
Okay.
But we delipidate it
Okay.
and we extract the proteins.
Okay.
And then these proteins are being printed on a slide that looks like this. It won't look much to you, but I will show you an image
Sure.
what is on that. So right now on this one there are 11,000 tumor samples.
Okay.
Okay,
11,000.
11,000. So
Wow.
it looks like it will take some time to load.
Sure.
So this machine that we got is able to print 1/1000th of a liter of the tumor.
Okay.
1/1000th. And it's able to use it from many different tumors. And so this one is this one.
Okay.
And each one of them, each dot what you see is the protein of a particular person. This is from one person, from another person, from another person, from another person, and you are able to check the level of protein expression of one person to another. But what we're mostly interested is that we always take both tumor material and healthy, normal, adjacent material.
Okay.
So we compare the level of expression in the healthy part versus the normal part. Now, we can do this for hundreds of proteins at a time. And if these proteins belong to the same pathway, then we can have an idea what is the flux of that particular pathway. So, and of course, humans are much more, they're much more when you use laboratory animals, they're inbred, so their genetic background is relatively the same. So there's not much variability. But from humans, there are male, female, child, no child, black, Hispanic, whatever. So you have a much greater variability, but there's power in numbers. Once you do this for 300, 400 people, and you check the same thing, then you start seeing differences. And this facility here, the capacity is 106,000 people, and this is usually for let's say approximately we can take material from 400, 500 hospitals that have the possibility for extracting a tumor, and that's approximately 7 countries. So this is the 7th facility in Europe what we are doing this. Yeah. MD Anderson has 3 such facilities. So MD Anderson is a main workhorse for doing such things.
Amazing.
Yeah.
So you're really able to crunch a lot of data.
Yes.
And see things that then are giving you clues in terms of what to look for and what to investigate further.
This one has a great diagnostic potential because some drugs work for some cancers, but not for other ones.
All right.
And depending on what proteins you see up or down regulated, you can decide what kind of drug to give or not. We don't yet do this, but we could do this. This is part of so-called precision medicine, patient-tailored medicine.
Right.
It will be possible to combine patient-specific therapy with metabolic aspect, because the metabolic aspect is not all the same whether the tumor is primary or secondary metastasizing, and in which tissue, and what about the metabolic profile of the patient. So there is some room to wiggle and adjust the metabolic therapy to the patient. That's also possible. Not to the extent as for the chemotherapy, but still it's also possible to do it there as well. This is an imaging facility.
So is this some kind of a dark field microscopy thing?
Yes. So in that they are live cells. This is a chamber for maintaining humidity and temperature, and we can follow their metabolic profile over 2 or 3 days.
So this is actually connected to the drug testing.
Yes.
So by the time you get something that you're looking at and then you have an idea of how to affect it, you would do the dosing of the chemo or whatever here, and you'd look to see how it actually interacts with live tissue.
Yeah, so when you have to go through many levels of checking. One is that you can check it on the isolated protein. Okay, then you go on the isolated organelle, in our case is mitochondria. Then you have to go in mitochondria with its natural environment, and that's the cell. So you have to check it in cells. And then you can go into more complex systems, like for example, a whole tissue or a xenograft or an animal before going into primates and humans. So there is a protocol.
Has any of your research gone that far? Into primates or
no, not
just
yet.
Mouse models is
Yes.
far. Okay.
Yes.
Good.
Okay, thank you very much.
Thank you very much. For now, for the Moss Report, I'm Ben Moss. How are you healing today?